Hello everyone, this is part 2 video on catalysis. In this video we will be covering the idea of shape selective catalysis, of which zeolites are one very good example, and the enzyme activity. So these are the two things that we will be covering in this particular lecture. Now when we were discussing about the characteristics of catalysis, we talked about the selective nature of catalysts. We even saw the example where the reaction between carbon monoxide and hydrogen, depending upon the type of catalyst that we choose, it was able to yield a variety of products. Not just that, the use of a particular substance as a catalyst will be limited to specific reactions. It is not like, say for example, we are using platinum as a catalyst in the hydrogenation of oils. We cannot be using platinum as a catalyst, though it is a metal having surface. We cannot be using it as a catalyst in each and every reaction. So the use of a particular substance as a catalyst will be limited to the specific reaction. So we talk about the selective nature of the catalyst. And one very extreme example of that is the shape selective catalysis, of which we will look at the zeolites to be one of the examples. So what is this shape selective catalysis? If you look at a catalytic reaction, that depends upon the pore structure of the catalyst and size of the reactant and product molecules. So the catalytic activity is depending upon the pore structure and size of the reactant and product molecules. So this selective type of catalyst, which is based upon the shape, is called as shape selective catalysis. Now zeolites are one very good example, because they have a peculiar honeycomb like structure which enables them to act as a catalyst in a particular reaction where the size of the reactant molecules will match the shape and size of the pores of the zeolite surface. So if you look at the zeolite surface, they have a microporous nature of the aluminosilicates with a 3D network of silicates. Silicates are SiO-Si. This kind of an linkage is what we call as silicate linkage. And if we look at the zeolites, one of the silicon atoms will be replaced by aluminum. That's why we call it as aluminosilicates. So they'll have AlOSi kind of a network framework. And the microporous nature on the surface of it will enable the zeolites to act as a shape selective catalyst. So if you look at the zeolite activity, the reactions where the zeolites are playing the role of a catalyst, the reactivity will depend upon the size and shape of the reactant and product molecules, as well as the pore and cavities of the zeolite. So where the size and shape of the reactant is exactly able to match the pore or cavity on the zeolite surface, we will see that the catalytic activity will be best. And the zeolites are some of them naturally available, and some can be synthesized for specific requirements, where we will be looking for very selective catalytic activity. Like one of the common zeolite, which is ZSM5, it's a commercial name, which is an aluminosilicate with 16 water molecules. The zeolites that we use widely are in particularly the petrochemical industries, where they will catalyze the cracking of hydrocarbons and isomerization reactions. Cracking of hydrocarbons is basically converting one hydrocarbon into another hydrocarbon. Usually it will be the larger hydrocarbons, they will be divided into smaller hydrocarbons. And isomerization is converting one form of isomer into another form of isomer. So these are the two specific reactions where the zeolites will be used as a catalyst. And the ZSM5, which is a commercially well-known zeolite that is used in the petroleum industry, it is used to convert alcohols directly into gasoline. So gasoline is petrol. The alcohols, large alcohols will be directly made to convert into gasoline, and this is done by dehydrating them. Alcohols, dehydrating means they will be losing the water molecules, and that is going to give a mixture of hydrocarbon. Mixture of smaller size hydrocarbons will come as a result of it. So that is the catalytic activity of ZSM5. So whole the activity of zeolites will depend upon the matching of the size and shape of the reactant molecules with the pore structure and pore shape of the zeolite cavities. Now the next important idea with regard to catalysis is the enzymes. Enzymes which catalyze biochemical reactions, most of them they happen in our human body as well. We call enzymes as biocatalysts because most of their catalytic activity will be for the biochemical reaction that happen inside the living bodies. So if you look at some of the common enzymes that we will encounter around us in some of the familiar reactions, as well as some of the reactions that happen inside our human body as well. Invertase is a popular enzyme that comes from yeast, and it will convert sucrose into glucose and fructose. Zymase, that also again comes from yeast, it will convert the glucose into ethyl alcohol and carbon dioxide. So in the fermentation of sucrose, both these enzymes, invertase and zymase, which comes from the yeast bacteria, they will be able to convert the sucrose finally into ethyl alcohol. So that is the fermentation reaction, and we see that in fermentation reaction carbon dioxide gas will be released. The enzyme diastase, which comes from malt, this will be able to catalyze the conversion of starch into maltose. And the enzyme maltase, it will convert maltose to glucose. So maltase also comes from the bacteria yeast. And urease, which comes from soya bean, it will break down urea. So urea is NH2 CONH2. It will break down urea into ammonia and carbon dioxide. Pepsin, this is the enzyme that helps in the digestion of food inside our stomach. So pepsin, which is present in our stomach, it will break down the proteins into amino acids. So these are some of the common enzyme activity that we see around us as well as within our human body. Now while we have talked about the characteristics of catalyst, there is some specific nature of the enzymes. So enzyme catalytic activity will have some peculiar characteristics which will make it different from the rest of the catalytic property. So if you look at the enzyme activity, generally when we talk about the heterogeneous catalysis, it is a surface phenomena, and what we observe is that the particles of catalyst on the surface only will be able to play the catalytic activity. The particles which are within that bulk, they will not be able to facilitate the catalytic activity. But if you look at enzyme, in most of the cases the enzymes, the colloidal state of particles will be the state in which the enzymes will be present, and each molecule will be able to play the role of a catalyst. So the catalytic activity will be enhanced so much that each and every molecule of the enzyme will be able to act as an catalyst. So this mechanism will be the most highly efficient mechanism. So if you look at the catalytic activity per unit mass of a catalyst, we will see that the enzymes will be standing at the top, because here each and every molecule of the enzyme will be able to act as a catalyst, where it can transform even like millions of reactant molecules per minute. So it is one of the very highly efficient catalytic process. There will be no molecules within the bulk that are not playing a role in the catalytic activity. Each and every particle can play the role of a catalytic activity. And the other important differentiator is that this is highly specific in nature. While generally itself the catalytic activity is specific because there is an chemical adsorption between the reactant molecules and the surface of the catalyst. But when it comes to the enzyme activity, it will be even more specific. It will be very specific. So each enzyme is very specific for a given reaction. So one enzyme cannot be able to catalyze the other biochemical reaction. So if we look at one catalyst, it will not be able to catalyze more than one reaction. Like if you look at the enzyme urease, it will catalyze the hydrolysis of urea only. So it will not be able to catalyze the hydrolysis of any other amide. So the catalytic activity will be limited to a particular reaction. So this is we'll see once we talk about the mechanism of the enzyme activity, we will be able to understand why this highly specific nature of enzymes is coming. The third important characteristics of the enzyme activity is that while the chemical reactions, we talk about optimal conditions for getting high yield in terms of high return of product. The enzyme activity as such for the biochemical reaction will be happening to a large extent under optimum conditions of temperature. The rate of enzyme reaction will become maximum at a given temperature or definite temperature, and this is what we usually call as the optimum temperature. Now on either side of the optimum temperature, what we see is the enzyme activity will be decreasing, and the optimum temperature range for enzymic activity will be generally in 298 to 310. So we'll see that this is the range of the human body temperature. So our human body temperature will be in the range of 310 Kelvin, and this suits the enzyme catalyzed reactions. Like if the body temperature is way above or way below, then what we would be seeing is that the normal enzyme activity will not happen at the optimal level, and that can slow down the biochemical reactions, and that can slow down the metabolism or the activity inside our body. Not just the condition in terms of temperature, but the biochemical reactions which are catalyzed by enzymes, the activity of the enzymes will also be optimum under particular pH value. Like if you look at the rate of enzyme catalyzed reactions, it will be maximum at a particular pH. We call this as optimum pH, just like the optimum temperature, and usually it will be in the range of 5 to 7. So if we look at the solutions where the pH is 5 to 7 at room temperature, then we talk about them as mildly acidic solutions. pH less than 7 means it will be acidic, but it is not very much less, it is slightly less than 7, so it will be mildly acidic solutions that will be able to have a high enzyme activity. So this is in terms of the dependency of enzyme activity on temperature and pH of the solution. And just like the way the catalytic activity can be enhanced by promoters, here the enzyme activity can be increased in the presence of what we call as activators and coenzymes. So there is a small difference between the role of an activator and role of an coenzyme. Now if we look at the coenzymes, then what happens is if we have the enzymatic activity increased in the presence of certain substances known as coenzymes, then what we see is that even if we have a small non-proteins, which are vitamins generally, present along with an enzyme, then the catalytic activity will be enhanced considerably. So if we talk about any small trace of non-proteins present along with the enzyme, then we'll see that if that is able to enhance the activity of a catalyst, we'll call that particular substance as the coenzyme. On the other hand, activators are generally the metal ions. Like if you have sodium ion, manganese ion, cobalt ion, copper ion, these metal ions, when they are weakly bonded to enzyme molecules, they will be able to increase the catalytic activity. So when the metal ions are weakly bonded to enzyme molecules, they will increase the catalytic activity. Like amylase, if it is in the presence of sodium chloride, the Na plus ions will be catalytically very active. Like the attachment of Na plus ions to the amylase will make the amylase catalytically more active. So this is about the idea of coenzymes and activators. So coenzymes are basically the small non-protein substances, small amounts of non-protein substances which will enhance the catalytic activity. Activators on the other hand are typically the metal ions. When present with a suitable enzyme, they will be able to enhance the enzyme activity. So the activators are more like promoters. Talking about the inhibitors and poisons, like if you look at the catalyst, we talk about the inhibitors and also poisons. Similarly, the enzymes are also inhibited or poisoned by the presence of specific substances. And what happens here is the inhibitors or poisons, they will interact with the active functional groups of the enzyme surface. So we'll see that the enzyme surface will have some active functional groups, and that is what is going to be making the enzyme activity to be coming into picture. And what these inhibitors or poisons will do is they'll often reduce or completely destroy the catalytic activity of the enzymes by engaging with these functional groups. Like if you have the use of drugs, generally this is related to the action as an enzyme inhibitor in the body. Like say if there is an particular catalytic activity that is going on which is harmful to our body, then specific drugs can actually go and act as an inhibitor or a poison, where they will destroy the harmful biochemical reaction when happening. So this is about the idea of inhibitors and poisons. Now coming to the mechanism of the enzyme activity. So what makes the enzyme activity so special in terms of being very efficient and being very specific in nature? The enzyme activity is based upon the shape of the enzyme or biocatalyst molecule. Like if you look at the diagram over here, we can see that the enzyme or biocatalyst molecule has got a particular kind of a shape. The substrate or the reactant which has got a complementary shape only can come and attach to form the enzyme substrate complex, and this is going to be depending upon the complementary shape of both these molecules. That is the reason why the enzyme activity is very selective in nature. Like it can only be able to act as an catalyst when we have a substrate which is having a complementary shape. And once the enzyme substrate complex is formed, if the reaction leads to formation of products, and products will not have complementary shape, so the products will leave the enzyme, and we'll see that from the substrate or the reactant stage we are able to get the product will be leaving out of the enzyme. So this is the broad mechanism of how the catalytic activity will happen. And talking about the specifics, if you look at an enzyme, there will be a number of cavities present on the surface of colloidal particles of the enzyme. So each and every particle of the enzyme will be able to act as a catalyst. So these cavities are of characteristic shape. Like the way we are seeing, these cavities will be having a very characteristic shape and possess generally active groups such as NH2 group, COH group, SH group, OH group. So these are chemically active groups that will be present in the cavities, and these will usually act as the active centers. So active centers means these are the chemically reactive sites on the enzyme molecule, and the molecules of the reactant which have complementary shape, they will fit into these cavities just like a key will fit into the lock. So only the molecules of substrate that have complementary shape, they will be able to come and fit into it like a key fits into the lock. And the overall mechanism we can see to be happening in two steps. The first step is the enzyme and substrate they forming an intermediate complex, and the decomposition of the activated complex will give the products which will leave the enzyme molecule and go away. So these are the two steps that will be involved in the enzyme activity, and we can see that clearly why it makes the enzyme activity very specific. Only complementary shape molecules can actually come and lock into the enzyme. And the reason why it is very efficient is because here each and every particle of the colloidal solution of the enzyme will be able to act as an catalyst. So if you look at what is the output per mass of or output or the activity per mass of a catalyst, we'll see that enzymes will have the highest value for that. So this is about the idea of mechanism of enzyme activity. So with this we have covered the shape selective catalysis and the enzyme activity, and in the next video we'll talk about the idea of colloidal solutions.